Okay, so again, good morning. Thank you everyone for coming. And the paper that we are going to be discussing today is this one: do explanation, explain, model knows best. So the subject today is about how to evaluate attribution methods, right? So, like I was saying before, my thesis is on ordinal data, on deep learning techniques for ordinal data in general. So when I contacted Professor Jaime about doing the internship here, he suggested doing something on activation maps or attribution methods. So this was very in line with my subject, because I work a lot with doctors, a couple of projects, and in this field, like, interpretability is very important, as you all know. Visual explanations then let the user see if the model is really looking where it should be, or just lets it know where it's looking at, right? So for this collaboration, we have this challenge of how to incorporate the ordinal information in the methods. But before even starting with that, we first need to evaluate these methods, right? How do we evaluate how good an explanation is? That's one of the starting points that you need to do with this kind of work. How are you going to show that your method performs better or worse, right? So that's why I stumbled upon this paper from this year's CVPR. Do explanations explain, model knows best. So what's the problem that we are trying to solve with these attribution methods? Well, we are going to solve the problem of feature attribution. So in this case, the model focuses on convolutional neural networks, and we are trying to we need to find which features are important for the output, right? So there are a lot of possible solutions in the literature for this. They are called a lot of names. They are called explanation methods, attribution methods, saliency methods. They are not exactly the same, but they are very similar, this terminology. I'm going to use the term attribution method in this talk, but there are some caveats. And the authors of the paper group them in this case in these 4 groups. So backpropagation methods, which is like backpropagation of the gradients for computing these attributions. Perturbation methods, which rely on changing a bit of the output, like nudging it or adding noise to see how it behaves. Latent feature methods, which look at the intermediate activations of the network to see what it's looking at. And also there's methods that use this shapely value metric, which from game theory, so we can look at features as players in a game, and the output of the model as the score, and we can see what happens when we take out features and such. So we have a lot of different methods, but every one of these methods gives us a different explanation. So why does every solution look different? Because, for example, this image from the IBA paper, we can see that in each row we gave the model a sample image, in this case a ResNet model, and this is what these 5 attribution methods tell us for what is important in the image, right? So for example, this top row, this is what GradCam tells us that's important for classifying as this breed of dog, right? But we see all these different attributions, some of them even have negative values. So we need a way to evaluate the performance of them. So one idea that it's present in the literature a lot is, well, let's just compare it with a round truth, right? We have maybe a data set with bounding boxes. So maybe we give the image on the top left, and we ask the model, okay, what's in this image? And the model says, it's a fox. And then we tell it, why is it a fox? And we want the attribution that the method gives us to be inside the bounding box, for example, right? That would be a way to test it. This has its problems. It's costly. It's tied to a given data set. So the attribution method may work well with that data set, or it may not, or vice versa, right? And also maybe what the model is looking at is not exactly what humans are looking at. This is maybe a little bit controversial, because we want the attribution method to be interpretable, right? But maybe we should also be thinking of that. Another idea, which is very popular, is start removing features from the inputs and see how the model behaves, right? This is like an evaluation study. This also has its drawbacks, because what if we have two features which are repeated? So they saturate the output, both of them. So if we, in the previous image with the foxes, imagine that we block this part of the image and the output doesn't change, because you can still see the rest of the foxes. Maybe that method says, okay, this feature is not important, but it is, right? So this kind of metrics may not even detect some of the objects in the image. Another idea is, well, just prove it mathematically, right? It's grounded in a proof, then it works all the time, but that's just not right? Reaching these general conclusions is very difficult. You have to make a lot of assumptions about the network, about which type of activations they have, and even when you when those assumptions are true, the implementations a lot of the time they break down, because maybe some approximation with a Taylor series doesn't hold really well because of the range that you're working on. So yeah, I like this quote from Linus Torvalds. So when theory and practice clash, practice always wins, right? So the authors say, why don't we just ask the model, right? Instead of relying on some data sets, instead of relying on all of this, let's create our own synthetic samples, our engineered samples that have the properties that we want to test from the attribution method. So what they do is that they freeze the model parameters, you can change them, but they try to create this artificial image. How? By optimizing like a patch of the input so that it has certain characteristics that we will see now. And the way they do this is not like they optimize the input pixels directly. They do like a deep image prior. So they input some noise into a decoder, and they optimize the decoder parameters to create this. But the details are in the paper. And then once we have this input images that we know that hold some properties, let's test how the attribution methods do, right? So, for example, one scenario that you might want to explore is the null feature. A null feature is a feature that doesn't contribute to a certain output, right? So this is like the mathematical foundations. We have a set of features, and a feature is null if that holds, right? It doesn't matter if it's in the input set or not. It shouldn't affect. So the way I like to see this is if we have an image with, for example, a dog and a cat. We note this as such. So this is composed of the background and the two features, the dog feature and the cat feature, right? So when we ask the model, explain to me the output for the dog class, this is what we will get. This map here is like with color on top of the image. And we want the explanation of the dog feature to lie only on the patch where the dog is, right? We don't want the attribution method to give it to the null feature, which was the cat. So the way they set this up is, okay, let's start with an empty image. In this case, a baseline image. They use an image with noise. They argue that it doesn't matter if it's an image with noise or an image that is completely black or white. I think that should be investigated, but we can discuss it later. And they try to optimize these two patches, the patch for feature A and the patch for the null feature. So feature A they associate with output A, and the null feature they associate with some other output B. But they make sure that it is a null feature for output A, right? So they have to solve this optimization problem, the double optimization problem, where we want to optimize the loss for class A for the feature A, but for the null feature, we want to optimize it for the loss of the B output. But we also have this term where its presence or absence shouldn't affect the output of the network, whether it's with the A feature, whether it's alone. And because we have created this image from scratch, we are able to remove these features as we want and test if that is true, right? We can just substitute each feature with the baseline noise and see that this truly holds. So that's how they stop the optimization for the generation of the synthetic input. And so, how do we test if an attribution method is performing well for this sample? Well, we know exactly where the A feature is and where the null feature is. So we want all the attribution to lie within the A feature, because the B feature shouldn't be at all contributing to that output. So this is what we see as an example in the paper. They have generated this synthetic image. So this is like a weird dream of the output you could think of. And these are the different attributions that each method gives. So in black is where the method says that it's most important. So in this case, what we want to see is something like what GradCam does, which is that most of the attribution lies within feature A, right? And we don't want any of it to lie within feature B. Because a very prevalent thing with these kinds of methods is that a lot of them, they don't really find relevant features. They only find features in general, right? Whether they are important or not. And we see that with some methods, with like full grad attributes, whatever, to all the image. The ones that behave the best for this scenario appear to be GradCam, IVA, extremal perturbation. IVA introduces like an information bottleneck in the middle of the network, and extremal perturbation tries to find like the smallest region that drops the output the most. So that's how in general they work. And they just run this like 1,000 times, and they compute the metric that we saw here, and that way they can rank how good they do, right? And so those three that I mentioned are the ones that appear to work the best in this scenario. Another scenario that they test is class sensitivity. So if we have two contributing features, and each of them contributes to a different output, we don't want the attributions to mix up, right? So if we want the attribution for dog to lie within the dog feature and the attribution for cat to lie within the cat feature. So they pose two different scenarios for this axiom. In the first one, they try introducing two features, right? So this would be similar to the previous example where we had two features, but in this case, they make sure that the A feature doesn't contribute to the B output, right? So this time they're doing it for both of them. It's still a double optimization problem, and this time what they are trying to what they're monitoring for the different attribution methods is this metric. So it's a little bit weird, but in general, if we have the attribution the attribution for class A and the attribution for class B, we want the attribution to lie within the features. But if we take the minimum of them, you can imagine the ideal attribution would be like all the attribution for A lies within feature A and all the attribution for B lies within feature B. So the minimum, the element-wise minimum of both would be 0. So something like this, right? This would be the attribution for class A, the attribution for class B, and the minimum of those would be this one. So we want the sum of these two patches to be as small as possible compared to the sum of these two, right? Ideally, it would be 0, and in the worst case, it would be 1. So that's what they test with every attribution method. And what we want, again, is something like what GradCam does, which is the A class attributes it to the A feature and the B class to the B feature. GradCam++, for example, fails with one of them, right? It attributes the B class to the A feature here. And the other two that I mentioned before, IVA and extremal perturbation, appear to do well too. So this is another that is difficult for these methods that only find features, whatever they are, because they just find the two and that's it. But they also tried this other one, which I think might be more interesting. Well, they only introduce one feature, but it's supposed to be no, right? It's supposed to be no for output B. So when we look at the attribution for output B, we should see, they look at this correlation between the attribution for A without feature A and the attribution for B without feature A should not be correlated. So we want this to be as small as possible. So we want to look at the ratio between the blue part and the red part, and these two ratios should not be correlated. That's what they are looking at. So what we want is, for the A class, we want it to lie within the A feature, and for the B class, we want it to lie outside of the A feature. So again, RedCam does a little bit worse, but mostly works. But the rest appear to don't know what to do. I think this is a hard scenario because most of these methods have some constraint at the end where they normalize from 0 to 1 the attribution, so they have to attribute it to something in the end. And if there's nothing to attribute it to, for the B class, for example, it will do something like this. In this case, RedCam does good because we made sure that it should be a no feature for class B. So it's none of the attribution should lie within it. Okay, but still the rest of the methods don't really know what to do for the class B, so they are attributed to feature A. And the last scenario of the test is this feature saturation scenario, where we have multiple features that are assigned to the same class. So feature A1 and A2 contributing to output A. So this would be like the foxes that I showed earlier. So all the foxes would be, each fox would be a feature, but they are all associated with the same class, right? So in this scenario, we want the attribution to be given to all of them because they are all contributing to the output, but not only one of them, or they all should have the same attribution, right? So here they test again with two features, but this time both of them are associated with the same output, and whether one of them or two of them are present, it shouldn't change the output. So the output is saturated, right? So in this case, again, we look at this metric. In this case, we want the attribution of class A for the feature A1 and the attribution of class A to the feature A2 to be correlated. This time we want it to be highly correlated. So again, we want something like what RedCam is doing. That's RedCam appears to be very good, which is good because a lot of people use RedCam. And this is a very easy scenario as opposed to the last one, because here we only have two features and both of them should be attributed, right? So in this scenario, any method that just search for features is going to do well. So I think that it will be more interesting, we can discuss it now when I finish, to have a third feature that is not associated with them and see that the methods don't attribute it also to the third feature. But I imagine that this must be difficult because we already have a multi-objective optimization to create the input image. So adding a third objective would probably be quite difficult. So those are the 3 or 4 scenarios that the authors test. And in general, they find that most attribution methods, like we can see, or most of those that they have tried, only find features, not relevant features, so they point at everything. These 3, RedCam, IBM, and perturbation, appear to work the best, with some caveats. Again, I didn't show the tables because here in the presentation I don't think it's relevant. You can like look at the paper, but the thing is we have like hard data. We have a metric that we can look at, but they have some caveats. Like we saw, some of the methods break down for some of the scenarios. But I think that the takeaway from this paper is mostly the framework. I think this is a powerful idea that we can use to test other methods that we can come up with. I think it can be difficult to devise some scenarios where we have more than two features that we want to generate, but I think this can be worked on. I think it was interesting in the sense that it's a data agnostic method, right? The model, they say they have used a model trained on ImageNet, but they argue, again, I think it would be interesting to see what happens. They argue that the model could be completely random, really. It just needs to hold those constraints that we put on the optimization problem, and that's it. It doesn't need to be anything that a human really knows what it is, right? So I hope you found it interesting, and thank you for your time, and let's have a discussion about it. Thank you.